you. We had a couple folks that aren't going to be able to join us, so we'll get that recorded for them. I should be able to offer the slides as well for download at the end. Hopefully I did that right on this to offer that. If not, I can always follow up with an email for anyone that wants to view the slides later. So again, thank you all. My name is Josh Cavender. We're going to go ahead and get into it. Gorgeous picture of myself there. My favorite topic. I've been in the technical, the concrete industry for, hold on one second. Let me make sure we got everyone muted here. I'm going to go ahead and mute the audience. Okay, so hopefully you guys can still hear me. You should be able to shoot me a text in the chat box if you have any questions or issues, or you can, I believe you are able to unmute yourself if there's any other technical issues or if you have a burning question. We'll try to get to questions towards the end, and hopefully this shouldn't take more than 40-50 minutes to get through this topic, and then we'll all have a chat at the end. So thank you again, everybody. If you can't see my screen, just shoot me a comment or something, and we'll see what I can do about it. Again, so going back to me, my favorite topic, 20 years of experience. Most of it is in ready mix. I do have some experience in admixtures, aggregates, and a little bit of technical sales. My position here at Cemex is sort of a technical sales role. It's technical services manager. I'm in charge of any quality issues or technical issues or consulting with regard to concrete or our cement products. I'm also responsible for the cementitious materials like slag that Cemex imports, and then I also have a role in technical support for the admixtures. All right. So the topics that we're going to cover today, mixed designs are really broad topic, so narrowing its focus was difficult, but I'm going to cover the sort of the raw materials. I'm not going to get too deep into the weeds on the materials themselves. Does somebody have a question or comment? Just checking here. We're going to talk about the materials, so cement, SEMs, aggregates, admixtures, all those things. Then we're going to cover some of the metrics that we use to coordinate those materials, proportion, things like that. And then I'm going to cover a couple of basic methodologies that ACI offers, ACI 211, and then an additional proportioning method that's a technical document from ACI. Just to talk about the general procedure for doing a mixed design.
Good morning, Josh. This is David. We're having some difficulties with the Skype meeting link. Is anybody else experiencing that? Maybe just our computer system.
Is anybody else having any problems? Hopefully.
Like just us. Okay. Well, we'll try to follow along. Thank you.
Yeah, I mean, I will try to provide slides, and this is being recorded so that maybe that'll help at the end. I can send that to you guys. Apologize for the difficulties.
That's your fault. Thank you.
So a lot of the topics I'm going to talk about, the material can be found in a couple different sources. The picture here on the left is the Portland Cement Association's Design and Control of Concrete Mixtures. This was the first book handed to me when I started in this industry and technical. It's sort of the Bible of mixed design, all things related to design and materials that go into it. And then on the right, I'm going to refer to a couple of different journals and standards written by American Concrete Institute that you'll see later on. So these sources are available if you want to dive even further into it. It's going to be kind of high level. I didn't want to get too technical. We could be here all day, and our eyes could cross with all the different. Okay, Jose says nothing's showing on the screen. Anybody else having that problem? I might try.
I can see it, but I don't know about others.
Okay. Anybody else having that issue? I will try. Okay,
we have a comment that others can see it, so I think it's more of a isolated issue.
Okay. Sounds like you have to download the Skype app. That may help it. Okay. All the issues with technology. You know, I'm not the most adept at Skype with business, and I'm not even sure this is the best platform, but hopefully we can manage through here. All right, so let's move on here. Talk about materials. Again, a lot of this stuff is pretty common. I'm not going to go too deep into the weeds here when I start covering some of the things, but we'll talk a little bit about each of these materials, how they affect mixed designs, and what's available, stuff like that. First thing we're going to talk about is cement. Cement's probably the most important ingredient in a concrete mix design. Also most costly. It's responsible for a majority of the performance in the mix. There's a couple of different types of cement available in the California market, type 2 and type 5 being the most common. There are about 5 different types that are spelled out in ASTM C150, which is the standard specification that defines how we produce Portland cement. Type 2 and type 5 are both related to sulfate resistance. Type 2 is a moderate sulfate resistance, and type 5 is a severe sulfate resistance. And what that is just the chemistry is restricted in such a way for the cement so that it doesn't respond to sulfate attack. C3A is the ingredient in cement. It's a tricalcium aluminate that reacts with sulfate and causes expansion and deterioration. And so the ASTM standard sets limits for how much C3A can be in the cement. By nature, if you have a type 5, that limit is very restricted. It's a 5% C3A. Type 2 is 8%, if I recall. So you have just different levels of restriction for the same property. So if you have a type 5, you by nature essentially have a type 2. Sometimes that gets confused. Engineers specify only one particular type, like a type 2, and they get provided a type 5, and they don't understand why. I have to have that explanation on a regular basis. Another type of cement and a cement standard, ASTM C595, relates to blended cements. Blended cements are much more common in Europe, probably starting to become a little bit more common here in the States. Blended cements are where you take the Portland cement and you will blend right in with the cement either a fly ash, a natural pozzolan, or a slag or limestone. Europe, like I said, it's more popular over there, probably just for the fact that you can have less silo space. So you're just buying one product, cement that comes pre-blended with either your slag or your fly ash, whatever they're producing, and then you only have to put it into one silo. It gives you less control or flexibility with your concrete mix designs, but it saves you on silo storage. Cemex is now producing 1L. I think there's a couple other producers that are also making 1L. It's likely expected to become much more common and probably eventually will replace type 2-5. The standard does put similar restrictions on blended cements as that C150 does. There's limits on chemistry for certain properties. It's all there in C595. And when you're purchasing a cement, you can look at a couple of different factors. One of them is a mill cert. Usually the physical requirements are probably the most important area of a mill cert that you're going to look at. Many producers have the same type of, are required to report the same test results, list them in a similar fashion, so it shouldn't be hard to find. But the physical requirements are going to outline how much heat of hydration that the product puts out. Certain things like how fine the cement is ground. Those will affect how rapid your strength gain is, how much heat is generated. Your set times, the initial and final sets, those become important. If your initial and final sets don't have a lot of time in between the two of them, that doesn't give finishers or suppliers a lot of time to produce and ship and place and finish the product. So those could be a factor when you're looking at a mill cert. Fall set and air contents, those are, fall set, there's certain characteristics where once water comes in contact with the cement, starts to react, and it acts like it's going to set up and harden right away immediately. Sometimes, depending on whether it's a false or flash set, you can mix through it, but sometimes if it's not, so that could be problematic. So you look for those higher numbers better. So the ASTM standard sets a limit on what those can be. And then probably your next most important would be your compressive strengths. Different markets for cements produce different compressive strengths. Some of them will focus on strengths achieving in 1 to 3 days. Some of them don't care about early strengths and focus more on a later strengths of 28 days. Arizona market, for whatever reason, maybe because of the temperatures out there that they experience, that market tends to focus more on getting heavy strength early. So it tends to shift a lot of the strength gain in the 1 to 3 day range, whereas out here it's more of a 28-day focus in California. Another thing that a lot of people don't know about that is available from cement producers is the uniformity report. ASTM C917 is responsible for the requirements for this report. What this basically is the cement producer takes regular grab samples, whether it's from loading a truck or from the trucks themselves or from some other point or along the chain. They take these samples and they can make them composite samples, or they could just be one-off samples, but they test these for certain properties. In this case, I have compressive strength or mortar cube strength here for 7-day and 28-day, and they plot a running average of 5 and then the individual strengths over time. So this is something that you could request from a cement producer, and you can use that to correlate your concrete strengths to any fluctuations in production of your cement mortar cube. So this is definitely a tool that you can avail yourselves of. The cement producers make this available for you on request. You just have to ask for it. So moving on from cement onto SCMs. I'm not going to talk too deep about this. A lot of us know what each of these are. Fly ash and being probably the most common, and slag more so recently. Cemex is importing slag. Lehigh has some slag. So there's a couple different sources of slag now making themselves available to this California market. Natural pozzolan, I think, is available. Silica fume is available. Not very cost effective, but it is available for certain applications. One way to think of SCMs, each one provides different properties. You can think of them as like an aggregate proportioning of your grading. Some particle size are different as far as some are larger, some are smaller, some are more angular, some are more finer, depending on which SCMs you're using. This is a close-up shot of a bunch of different types here. And so you can see fly ash in the bottom right is more of a spherical particle, and it's much smaller than a cement particle. So it typically gives us flowability and fluidity out of our mix design with less water. So a lot of people like that because you can put less water in your concrete mixes and use fly ash. We all are starting to realize that fly ash is becoming much more scarce. It's based on burning coal. Coal has been kind of the redheaded stepchild. It produces a lot of CO2. It's getting reduced more and more. There's not a lot of coal power plants, so fly ash is becoming much more scarce. That's why we're starting to see things like slag cement come onto the market. You look over here on the left, it's similar to the Portland cement particle in the middle. It's a slightly smaller particle than Portland cement, and so that you can use all these things. Like silica fume is extremely small particles. There's many of them for a given unit of volume. These can be all used in conjunction with each other. Again, assuming you have silo space, that's always the problem, is storing multiple different types of SCMs on top of your Portland cement silos. But you can consider these as working beneficially with each other, fly ash and cement, or even silica fume and cement and fly ash, or slag and fly ash and cement. All these can be combined to get various properties from your concrete mix. So talking about aggregates, the focus of this talk is, and some of the mix design methods that I'm going to talk about later, is going to kind of revolve a lot around aggregates. I think aggregates tend to be mostly neglected, or the focus is on other things like naturally water cement ratios, cement sources, SCMs, things like that. You know, aggregates make up the largest proportion of a concrete mix design. They tend to have the biggest impact of a concrete mix. You know, their shape, their cleanliness, their grading. You know, if they have elongated, if they're angular, they can affect things like strength, flexural strength, workability, how well they pump, how well they finish, change the viscosity of a mix, change the flow rate, how well they go through congested members. Aggregates play an extreme role, and that's why there's a lot of different design methods and metrics that center around how we choose our aggregates, what proportions we use, and things like that. I put this slide in here just to kind of visualize how a matrix of aggregate may look in a mix design, and sort of a visual representation of how we're proportioning and controlling our mix design. So, you know, there's aggregate sources that are river rock. They're nice and smooth and granular. They'll stack really well. They'll make very fluid concrete, but the problem is they don't necessarily generate very good flexural strength or compressive strength because the aggregate system is rounded and sort of rubbing up against each other. Again, these portions or particles could become elongated, and that may help you a little bit more in flexural strength and water demand, things like that. Each of these different types of aggregates and their shapes and all that comes into play on how we proportion and how we design mixes, and they play a significant role. So moving on to admixtures, you know, again, this is not, we all know about admixtures. I think the most common would be the water reducers. A lot of concrete has water reducers in them, whether it's a low range water reducer. Some suppliers will put mid ranges. Some prefer small doses of high range or high range water reducers. These are becoming much more engineered. The polymer chains are engineered at various lengths to provide various properties to make the concrete more fluid, stay fluid longer, and things like that. So we all know about those. They come in handy when we're designing mixes for special applications, or great to just reduce the cost of our mixes by being able to reduce cement and water. Air entrainers, you know, we get those in there for durability. Not uncommon for suppliers to use an air entrainer to get a little bit more fluidity out of their mix design. You know, small doses of air entrainment help mixes that have really coarse sands or really sandy mixes. You can get a little bit of additional fluidity out of your mixes with a little bit of air entrainment. And you got to be careful with that and balance it, because, you know, each percentage of air you include into a mix design is going to reduce your strength, so you can find a balance on that. Then there's a couple other things that I just wanted to mention is slump extenders and viscosity modifiers. These are more specialized admixtures that help you do really crazy things like pump a mix that's very pasty mix 60 floors up in a high-rise building. Or if you have water, concrete that you need to pour underwater, or concrete with really poor manufactured sands, you can use viscosity modifiers. Those make the mix kind of, the best way to describe it would be give the mix more body, let it flow and be more cohesive. And those are seen commonly when you have a poor source of sand, or you need to do other things like make it hold together underwater. So there's a lot of different crazy things we can do with concrete that help improve mix design. So with that, I'm gonna move on to certain metrics. These are gonna be different charting diagrams and different tools that one can use to produce proportions for a concrete mix design. The Power 45 is pretty common. It was generated in the asphalt industry. I think that was its origin. What this represents is these dark lines, diagonal lines here, represent the maximum possible density for each individual sieve, going from whatever the maximum aggregate size you're using to the finest particle size in aggregate, number 200. Anything beyond number 200 or finer than number 200 is considered powder and starts to get into the cement and SCM side of things. So this is more of a tool that focuses on aggregate grading and proportioning. So this line, the green line, is our plot for whatever aggregate source we're using here. In this case, it looks like it's probably a 3/8 material, and so each percent passing works its way up the sieve here. And so if your line for your aggregate source follows this max density, that's optimum. That means it's the greatest amount of particle packing that you can have for that given material. Now, we don't always want to target exactly having our line follow the maximum density because we do want some fluidity and some workability out of our mixes. If we did target a mix where the max density lines up perfectly, you're going to have a very dense and very unworkable, unfriendly mix. That's probably something more geared towards a paving mix or something low slump that means max density, or roller compacted concrete. Things like that will generate really good dense compact mixes. Oops, I'm sorry. But in most other applications like ready mix and wet batch, we're going to probably want to keep it a little on the finer side. So the finer side would be towards the upper left. Anything that pushes above that line is pushing towards the finer side, and then anything that falls below that line is more of coarser. Another thing that you can use this chart for is it'll tell you whether you have any gaps in any of your gradings or any peaks or valleys. So if you have too much on a particular sieve, you'll see a peak in whatever sieve that ends up being, or if you see it drop off on the lower side if you have not enough on any given sieve. Another really common metric or chart, if you will, for determining your proportioning is the coarseness and workability chart. What this does is sort of box out and provide certain zones that correspond to how your mix behaves, whether it's workable, sandy, sticky, or geared more towards rocky and coarse. So you would plug in your gradings, your combined gradings, and without getting too much into how it's calculated, the workability factor is the percent passing to number 8, and then 2.5 times every sack above 6 sack. So everything passing number 8, so all kind of the fines it focuses on for the workability factor, and then it includes high cement sack mixes as well. And then the coarseness factor is your percent of cumulative percent retained for the 3/8 divided by your cumulative percent retained for the number 8 screen. That's how you generate these two numbers, and then it gets plotted here on this chart. So you may, let's see here if I could do the pointer. So you may end up that you have a plot point like right around here, and then you know that your mix is probably over sanded. It'll include the cement powder, so maybe it's over sanded and over powdered. So you can change your properties of your mix and drop it sort of down into the well-graded area, which is considered this kind of zone here. And you may even see this chart divided up even further into individual zones within the well-graded portion. So a lot of different modifications of this type of charting. And then over here is your 3/8 and half-inch zone. This is where typically a 3/8 mix would land, or a half-inch mix. And then if you're kind of in this zone, you got to be concerned with gap grading issues. So that's kind of how this one works. A lot of studies and research on this tend to show that this is not very accurate. It's the charts we're going to look at next tend to be more favorable based on a lot of the testing done. It's shown that the results you get in the field don't correlate as well with this chart as some others. Percent retained, this is a very common chart. In fact, there's a lot of job specs that I saw in my past that specify this. They'll provide, so what this is it shows the sieve sizes, fine to coarse, and it charts the percent retained on each of those sieves, so how much particles were retained or mass retained on each of those sieves. And then it sets a barrier for the upper and lower bounds of those individual sieves. And this chart helps you in determining whether you're missing anything on a particular screen or you have too much on a particular screen. So again, I think this is charting, this black line is charting like a 3/8 aggregate. So you see that it's, from the fine side, it sort of steadily rises until it reaches a peak of number 4 size particles, and then it sort of drops off to the 3/8 size particles. This is pretty common for a 3/8 grading percent retained. This is often modified. Sometimes it's even stricter. It's like 18 is the upper limit to 8 at the bottom, or sometimes you'll see it like this as 22 and 8. But this will show you a profile of your aggregate grading and lets you see any peaks if you have excessive amounts of any one particular particle. Now, if you have more than a couple of screens that drop off or have too much on them, that's a problem. Generally, when you have like one screen that peaks or drops, that's probably not going to be too critical. The two screens on either side of it will help carry it. But if you start to have more than one sieve, consecutive sieve size that has either an excess or too little, then you might see issues in your mix of being gap graded or segregation problems, just because there's not enough body to carry all of the concrete or the paste. All right. This is an evolution of the 8 to 22% retained screen. This is called a tarantula chart, just for how it looks like a spider. And it's basically kind of modifying individual sieves to have certain limits. You can see down here it states that kind of this region is not enough. You know, you're a little too low on your number 50s and number 30s, which are pretty fine particles, to get enough to make a decent mortar. And then you also want to be careful of going too far above to having too much of those particles, because then you're going to have a sandy or a sticky mix. So it starts to provide individual sieves certain limits, finishability problems, edge slumping. You know, some of these larger particle sizes, number 4, 3/8, and ½ inch. You need some of those to get enough to hold the edges together, to stack up on itself and hold itself together for the mix. But then you also don't want to have excesses of those particle sizes, because you'll have segregation issues. So this is just a kind of a modification of the 8 to 22, a little bit more sophisticated. And you'll plot your aggregate grading. Will come along here and try to keep it within these lines, these upper and lower bounds, by adjusting your proportions of your different aggregate sizes that you use. This is also a percent retained chart, but this is related to designing self-consolidated concrete. Typically, self-consolidated concrete are smaller maximum aggregate size, 3/8, ½ inch, maybe at the most. You need a lot of number 8 and number 4s to get a good body in the mix, and some good amount of fines so that the mix will flow. Self-consolidating, self-leveling, it flows around congestion, uses admixtures, and uses gratings to make decent concrete. So this is just another modification of the percent retained chart. So those are the metrics. And like I said, I'm going to cover a couple of different topics or different design methods. The most basic one is ACI 211.1. Let's see if I have it here. Standard practice for selecting proportions for normal, heavyweight, and mass concrete. These are available on concrete.org. I think they charge for individual PDFs of these, or you can pay for a service to get access to all of them for a year. This is a good starting point if you have no prior knowledge. You don't know your mix characteristics. You don't have prior existing mixes. You don't know your aggregate sources, how they behave, any proportions. This is the starting point for not having any body of knowledge to work off of. Generally, you're going to have a history of mixes and proportions that your company or supplier has used in the past. If you're a mix designer, that you can reference. So it's not very common that anyone goes back and refers to these ACI methods or standards, because they just start with existing mixes and modify those to get whatever properties they want. But that's why I wanted to kind of go through this, and then I'll show you another method that's a newer method that ACI put out a journal on. We'll talk about that. Before we talk about the design steps, it's important to note that there's two different types of ways of specifying a concrete mix design: prescriptive versus performance. I'm going to talk a little bit about what that is. You may even see specifiers combine prescription and performance together. They may have certain aspects of one and the other when they write their specs. So basically, prescriptive is the specifier states that they want you to achieve X water cement ratio. They want you to have minimum cement content. They may even specify how much SCMs and which types you can use. Admixture doses, things like that. They're essentially, the specifier is designing the mix for you, telling you what targets to hit and whatnot. Performance is that the specifier is stating that they want the mix to achieve a certain level of performance. They may state that strength has to be 5,000 psi, slump is 4-inch slump plus or minus, whatever. So that is performance-based mixtures. And now, like I said, you may see some specs where they just state, they want the mix to perform at 5,000 psi, but then they also state a minimum cement content and a water cement ratio, et cetera, et cetera. So you, like I said, you'll probably see some combination of the two. Now I included this in here. This is a reference to ACI 132R. It is the guide for responsibility in concrete construction. I've oftentimes, when I was in the design field, I'd have a lot of issues with some specs being either contradictory or having unreasonable expectations on the mix design. And so that's why I kind of wanted to include this in here. One portion of that document states that when the concrete material supplier contract contains only prescriptive requirements for the concrete mixture composition, the concrete material supplier has a responsibility to develop mixtures in accordance with the standard and care of the concrete material supplier. But it is not responsible for performance characteristics intending or resulting from the prescriptive requirements. So what this document basically states is that if they're going to prescribe the mix elements, they can't also make you responsible for the performance of that specified mix. Later on in that document, it also states in regards to a performance spec that when the concrete material supplier's contract assigns performance criteria to the concrete mixture, these criteria need to be clearly defined, and it is the responsibility of the material supplier to demonstrate compliance with the criteria set forth in the concrete material supplier's contract. In such cases, the concrete material supplier should have the right to retain confidentiality of the mixture composition. This is something that never really happens in the design industry. You spend a lot of research and development making a mix. Maybe you make a really well self-consolidating mix. You find the right mixture of aggregate source, a combination of admixtures, and you make a really nice SCC mix. And then it gets passed around from contractor to contractor or from supplier to supplier, and everyone just copies it. So there is certain circumstances, and sometimes it's very difficult. I think many years ago managed to convince LA County or LA City to accept a mix that just stated that certain standards, or that it's basically like a certificate of compliance. The mix stated that it complied with this, that, and the other thing standard for cement, for SCMs, for aggregates, but it didn't spell out any actual weights or any specifics of the mix design itself. We were responsible for the performance. They accepted the mix as it was, but it didn't have any specifics of the design itself. So it can be done. It's difficult in a lot of cases, but you do have some rights to confidentiality of your mix design, especially if you're doing a lot of research and development and putting a lot of effort into those designs. So moving on to 11.1, that document is going to have a step-by-step instructions of what you have to do to design a mix. It usually starts with getting the basic information down, such as, is the slump specified? Is there a maximum aggregate size specified? Those choices are going to depend on what concrete is being placed or used for. Elements of high congestion are very narrow elements. You can't pick a very large aggregate size, so you have to reduce your aggregate size depending on certain factors like that. The performance requirements that at the very least should be specified, or you should know that based on what the application is, whether it's a 2,000 psi backyard slab or a 9,000 psi column mix in a high-rise building. Those performance requirements should be spelled out. And then exposure is another common criterion. Durability, whether the concrete element is going to be exposed to a freeze-thaw environment, sulfate environment, or high chloride ion concentration environment. Those factors are going to come into play, and those will change how you determine your mix design. It'll change the water cement ratio requirements, whether or not you need to include certain SCMs into your mix. Those will come into play, and those will either be specified, or you should have some information on what those requirements are for your mix before you start. So in the document, the ACI has several tables that give you generalized information about where to start with your design. In this case, this table refers to the aggregate size that you chose, whether it's a 1-inch mix maximum, and then what type of slump you're targeting. So in this case, if we wanted a 1-inch mix at a 3 to 4-inch slump, it recommends that you start with 325 pounds of water. Now, again, if you have an exposure situation, mild or severe, moderate, you're going to have to increase your air content, add in air entrainment, and bump up the air. And that's going to reduce the amount of water you need in the mix. Because as I mentioned earlier, adding air entrainment into your mix adds some fluidity. All those little bubbles act like little ball bearings, give you some fluidity, so you don't need as much water in your mix design. So this gives you a starting point. Once you determine this, you can calculate your cement content from your water content, your water cement ratio in the next slide. So there's some general rules of thumb here for certain water cement ratios. You can, if you had 325 was our water content and we needed to get a 5.0 water cement ratio, then it'll tell us, generally how many pounds of cement we're targeting for that. And then on to the right here, it does give you some general information about, depending on the aggregate size that you use, larger aggregate sizes have less surface area, so they don't require as much water to coat them. On the other end of the spectrum, though, the 1/2-inch and the 3/8 mixes, they have a lot of surface area, a lot of particles in that aggregate, so they need a little bit more water to get the same fluidity. So this is a chart based off water content for slump that you're trying to target. It's going to shift depending on what your maximum size of aggregate is in the mix. So it provides you with some of these general rules that you can go by to design your mix from scratch. Here's a table of strengths. This is, again, how you determine the biggest relationship or the strongest factor in a concrete design for performance is the water cement ratio. How much water to cement there is in a mix design is going to determine what kind of strength you get. So these are generalized rules for, at a 4-inch slump, or a 0.41 water cement ratio, you're going to see 6,000 PSI concrete in general. Now, like I said before, and I'm going to emphasize that this is generalized. Your individual materials, different markets, different areas are going to have different cements, different aggregate sources. They're not always going to apply, but this is a good starting point if you had no basis. So you would determine that you say you're going to do a 4,000 PSI mix, you're going to target a 0.57, and then you can go back here and sort of interpolate to see how many pounds of water and how many pounds of cement that's going to be. Once you've got your performance characteristics, your cement and your water nailed down, then it's on to figuring out your aggregate contents. Coarse aggregate, you're going to start that first, as it's the most important probably factor for your design. And the way that ACI does the choice of coarse aggregate content, or how many pounds you're going to use in a mix, is based on your dry rotted unit weight. So you would take your coarse aggregate and you'd put it in a bucket, and there's a whole standard for doing this. It's ASTM C29, and determine the dry rotted unit weight of that aggregate. Then you'd also calculate the fineness modulus for your aggregate. Fineness modulus, again, is another way of determining how fine or coarse your material is. You add up a certain number of sieves, certain specific sieves, and divide by 100, and you get a factor. And it's usually a number between like 2.4 to 3. Generally, ACI limits mixes from 3. Anything higher than 3 as being too coarse. But you determine that fineness modulus, and then it gives you a factor based on whatever aggregate size you're using to apply. And then there's a formula that you use. So you would multiply, let's say if we're 1 inch, and it was a 2.6 fineness modulus, multiply 0.69 by the amount of volume that you're designing for. So in this case, a cubic yard of concrete is 27 cubic feet. Again, this gets pretty deep into all the calculations in the weeds, but ultimately it would give you an amount of aggregate. You do the formula, and you come up with, say, like 1,400 pounds of rock, and then from there you take that number. And if your design is based on SSD, which is surface saturated dry, basically the amount of water that coats the aggregate This result here is based on a dry weight. So if your aggregate had some moisture on it, which most of the time when you're batching concrete it does, and your design is based on that moisture that coats the aggregate, then you would want to increase your weight of your aggregate based on the absorption of water in the aggregate. It can get pretty minutia going down talking about all the specifics of that, but more or less you can change this from oven dry rock to moisture, include the moisture in it when you're doing your design. So then once you've had your coarse aggregate, the final volume left behind is anything for your fine aggregate. So you would choose your weight for your coarse aggregate, and then that would leave. So you'd have your cement, your water, admixtures. Generally, are not calculated into the volume of a concrete mix. It states in ACI that usually it's not a significant factor. If you do high volume admixtures, usually SRAs or admixtures where you have like a gallon or two per yard, then you would want to include the volumes of those admixtures into your mix design. So you would account for that volume and push out some other materials depending on how much admixtures you have in your mix. It's not a bad idea to consider calculating the volume of your admixtures in your mix designs. If you don't, you think about if every single one of your mixes has a water reducer in it, and you do 10,000 yards a year of concrete, it's probably around 0.2, maybe 0.02, I think. It's a small amount of cubic footage that you're giving away by not accounting for that admixture, and it can add up as a law of large numbers and multiple thousands of yards shipped throughout a year. That's all wasted volume. So it's something that you can consider when you're doing your design. That is basically ACI and 211, the very generalized way of doing a mix design with no prior knowledge. Again, if you have mixes that you already know perform, say you know that your 5:0 water cement ratio mixes at a 50% coarse aggregate and 50% fine are just fine all day long, you can just start with those mixes and make the mixes based on that. This is a general tool to do a design from scratch. So the other method that I wanted to talk about is this method here. It's called the aggregate suspension mixture proportioning method. Kind of a newer way of looking at mix design. I figured I'd provide the basic bread and butter way of doing it, and then talk about this little modified version of doing a mix design. So this method is suitable for anything from a normal weight concrete mix all the way up to self-consolidating, very flowable concrete. So it covers quite a wide range of different applicable concrete mixes. It's based on packing density, and it uses tested correlated data between your aggregate grading, your particle shape, size, and the angularity of the aggregates themselves. And it uses that to determine how much paste minimum you need in your mix. And then you add a little bit additional paste because again, like the bulk density or like the power 45 curve that we looked at before, you're not necessarily wanting to target a perfect maximum density for everything. You always want to pad it with a little bit extra paste or a little bit extra powder to make the mix a little bit more flowable, more fluid, easier to place. So it starts with figuring out a minimum paste to fill all the voids in between the rock, to provide enough suspension between rock particles so that they're not rubbing up against each other and causing fluidity issues or workability problems. And then it pads it with additional paste and it allows you to generate a different design. So it looks at two different types of, or it looks at a mix in two different ways. It's basically the aggregate system, and then that system suspended in paste. You select a aggregate proportioning. You use some of the tools I talked about earlier to determine what ratio of aggregate you want to use, or a proportion that you know works well with your local materials. Then you do some calculations to figure out what the minimum paste content is, and then you pad that paste content a couple percentages to get workability. And then you'd want to test and look at the characteristics and then retest maybe if you can to sort of fine tune and adjust your mixes so that you make an efficient mix, does what it's supposed to do, and then uses a minimum amount of paste to keep your costs down for your mix design. So a lot of the steps are similar for ACI 211. You select a maximum aggregate size. You determine a proportion using whatever metrics that you are comfortable with. You know, you can use the Power 45 curve. You can use a known ratio of aggregate coarse and fine that you've used in the past, and then you use a factor that the standard provides, or that the journal provides, for calculating a paste content based on the aggregate voids and the shape of the aggregates themselves. So in that journal, it talks about, it has a table here that lists kind of a factor that you would choose based on how you visually looked at your aggregate. If one tends to be a rounded river rock material, well-rounded, kind of equal dimensional, or from the other end of the perspective, you can have a source of aggregates that are very elongated, highly angular, crushed rock, something like that. You would rate it between 1 and 5, depending on what your materials, how it behaves. This test method also uses the dry rotted unit weight test, D29, but in this case, you would take your aggregate proportions and you'd fill this bucket up with all the materials together at the proportions that you chose, and get the density that results from that proportioning. That will then get used later in formulas to calculate your paste content. So this is coming back to that table that I showed before with the aggregate illustrations, but this is kind of how it's actually listed in the report itself. So once you would assign a value to your aggregates, and you would weight them by percentage that you use. So if you had 45% of an aggregate source that was like a number 3 here, you would multiply 40.45 by 3 to get a weighted average of the two materials. You do the same thing with your other aggregate source, and then you come down here and you get your minimum volume of spacing paste plus air. So this, if you're doing an SDC mix and your average of your aggregates is a 3 visually, you'd be about a 14% paste factor here, or 6% if you're just doing a normal 0 to 8-inch lump mix. So once you've done that, there's a formula that's in there. I spared you guys a big formula for calculating all this out. You can go visit that journal if you're more interested and wanted to look through it. So you do that formula, calculate out your percentage of paste, and then you generally would add 1 or 2% on top of that to get your workability and flowability of the mix. So once you've taken that and you've got a percentage of paste based on the volume that you're designing on, cubic yard, then you can back calculate and figure out, based on the other parameters of the mix, whether it's a 5:0 water cement ratio, or you have some exposure situations where you need 6% air, and then certain admixture doses to get your slump, you would go and calculate your weights and volumes off of that percentage, and then you do some lab tests and batch. One of the things that I don't see happen very often by suppliers or labs is when they do batch mixes, there's not a lot of visual inspection of the mix. They'll do the common air test, lump test, strength, cylinders, stuff like that, but they don't note anything about, what was it? Was it segregating? Was it coarse? Did it look real sandy or sticky? So one of the things to do is to go and observe your mixes, not only in the other test methods, but just visually inspect them. If it's an SGC mix, you often look for the halo around the outside of the concrete flow, or a buildup of rock in one specific spot. Same thing with a normal mix too. And then you can go and you could go back and adjust by either reducing your sand, increasing your rock, adding an SEM, or removing an SEM, reducing the percentages, things like that, or starting to add admixtures that will help provide a little bit more viscosity or something like that, so that you can improve these properties and fine-tune your mix, so that that you have the most efficient mix possible with the least amount of cement powder possible, reducing your cost but still getting the same performance. Because oftentimes you can meet all the requirements for a spec, but then you may have a really coarse, harsh pumping mix, and you don't find out until the product gets on the project, and then you have issues that you're having to deal with the day of. So also, it's equally important to do visual inspections of a concrete mix in addition to the normal test that you do. So with that is the two different methods and some metrics. So hopefully you guys got something interesting out of that. I will open it up and unmute the audience for any questions, or you can type something in the comments box there. And I think Michael has some final comments as well. He's gonna do. So any questions? Let me make sure that I'm.
We have a text question, and that was, what do you think affects shrinkage the most when designing a mix, or what are the most contributing factors in a mix in regards to shrinkage?
Well, with shrinkage, I think the most important role is going to be your water content and your paste content. Aggregates do play a large role in shrinkage, but ultimately, water. We make a mix with a certain amount of water so that we can place it and have it flow and deliver it, and then all that water has to escape, and that's a huge amount of volume that is released from what we started at to where it finishes in its place. That volume change is tremendous when it comes to shrinkage.
And
Any
Josh,
other questions?
On that note, I know the gradient aggregates don't play as big of a part, but I think I've heard before that by having gradient aggregates, you actually reduce a lot of paste filling those voids, and so that does help as well because it reduced the amount of paste.
Exactly. So that's kind of why I talked about that other method. If you can get your paste content to the point of the minimum amount you need to make the right properties for the concrete, then you are minimizing the total shrinkage of your mix. It's always a mitigating thing. We can't ever completely eliminate it just because we can't eliminate the physics behind it, but we can certainly take a lot of steps to reducing it by proportioning our mixes for minimum voids, by using the minimum amount of paste to fill those voids and still provide some workable concrete.
Perfect. Have another question coming in, and that would be, what items can we be prescriptive about in the specs to get low shrinkage?
The items you can be, so there's admixtures help greatly. So, that volume change that I mentioned earlier with the water, you have your SRAs, shrinkage reducing admixtures. Those can play a good role in that. You can specify certain aggregate sources, but that's a little bit tougher because some suppliers are only going to have certain sources available to them. So you can specify certain types of aggregates, like a limestone-based aggregate or something that shrinks a lot less. You can specify a certain dose of SRAs. SRAs usually stop becoming effective beyond 1.5 gallons per yard for the most part. So you get the most bang for your buck on an SRA at around 1 gallon per yard. That can be a way of reducing the amount of shrinkage. Lower water cement ratios by nature means less water, so you're going to have less shrinkage. So there's a few different things that you can do to reduce the shrinkage potential.
So from a specs standpoint, I've seen some specs put out that they actually have the shrinkage number cannot exceed XYZ. If they stick with something like that, that really does leave the contractor and the provider a lot of flexibility on what direction they go. Would that be correct?
Yeah, that's correct. That's probably the best way to do it. That's also the most common way to do it. You state a shrinkage per ASTM C157. It's in a percentage. Usually, you may set it at 0.04%. Sometimes even more extreme. I think Caltrans has a 0.032% for their bridge decks. Just note that getting into the 0.2s or 0.02s and 0.03s range is very tough for a supplier to meet. They have to start doing extreme things like really lowering the water content, making the mix real sticky with a lot of admixtures, using a high dose of SRAs, which can sometimes affect strength. So there's the more extreme you take that shrinkage number down, the less options a supplier will have. But yes, it's a very good way to do it. Gives them some flexibility and some choices for their design.
Yeah, one of the challenges I heard in the past was in designing the specs. They were trying to shoot for keeping, the options on the table for a cost-effective spec, because when you start using SRAs, things like that, you do increase cost. So they put a few specs in, but it ended up in one market, it worked perfectly. In another market, because of the sources available, what was available to them, it really sort of tied the provider's hands, and it ended up driving the cost up. And that's where I think that, if we keep in mind the less specific we get on aggregates and things like that, the better options we have for getting the results we want, getting the product we want, and getting it, at the most competitive price we can get it, because everything's different from one market to the next.
Yeah, that's a very good point. Sources of aggregates may play a role, and if it's an extreme shrinkage requirement, you might have to import from far distances to meet that requirement. You can only go so far with admixtures. You can only reduce the paste content so much. So yeah, it can make it tough.
Absolutely. Now, another question, and this is an excellent one. Really like it. When reviewing a concrete mix submittal, what are the top 3 items to review?
When you're looking at a submittal, so boy, that's a good question. I have so many ways I could take this. You're going to want to verify that first make sure that all the numbers are calculated right. Can't tell you how many. I use spreadsheets a lot. A lot of people use spreadsheets. There could be rounding errors or just plain issues, but you want to verify that all those numbers are correct. Your volumes are calculating right. The specific gravities, I think, are very important for the materials to make so, because they are basically bridge the gap between the person producing the concrete. So the guy batching it is going to weigh everything up in weight, in pounds or kilograms, and then the guy on the job site is going to be pouring it in volume. Sometimes specific gravities are out of date, they're completely off, or they're just an erroneous number in the spreadsheet. Those will throw off the volume of the concrete produced, even throw off the amount of a particular material in the concrete, making it maybe more coarse, more fine than it needs to be. So I think it's important that aggregates get tested regularly. So if they submit a C33 report, which is a report responsible for your aggregates, tells you their specific gravities, their absorptions, their gradings, all that stuff. If that's going with the mix design, to verify that the mix design has the same sort of data that's on that C33 report. So I think specific gravities are a real important thing to look at.
So we are hitting the 12 o'clock noon, everybody's lunchtime, so I don't want to hold everybody. I do want to make a couple quick comments, and then we're going to go back to questions for those that want to stay. Josh and I are willing to hang out as long as there's a need. One of the comments I want to make is if you are involved in setting those specs and being able to do prescriptive specs, just remember you can allow the providers and the contractors to do so much of your job for you by using prescriptive specs. Trust me, every contractor wants to win that job. They're looking for the best cost-effective solution that still meets the requirements. Same with providers. They want to win that job. So, that competition helps, in the end for getting the most cost-effective solution that meets those specs on the job. So don't forget, that with using that method, it can be a win-win for everyone involved, in private projects and public projects. And then the other thing, we do these weekly. In fact, just a couple weeks ago, we did one on competition. And so next week, right now, we have scheduled sort of a special identifying one area. The County of Butte has an engineer that is partnered with a pavement engineer from CNCA. They worked together for a lot of this fire recovery that was going on in the damaged areas. And they're going to talk a bit about how FDRC has been, a godsend for them in dealing with these roads that have been destroyed by all the recovery traffic, all the emergency vehicles, and how it's really, been an impact on them trying to piece back together things and put roads back together after this, the disaster that took place. And so next week that is scheduled. If there might be the Butte County engineer has one thing that may interfere with that, and we might have to bump it to the following week. But right now, that's scheduled for next Wednesday, and I will send out the invites again either tomorrow or Friday. And then we also have other topics we'll be bringing up for the following few weeks. If there's anything that any of you wish us to cover that you think will be beneficial for your team, we could do it one-on-one. We could do it in these Wednesdays. We're happy to take suggestions for topics to cover. The whole purpose of this is education and using this time where a lot of people are working remotely to help us all learn more about the field that we're in. So use us for that. And then as well, the team that I'm with, we're happy to help with going on beyond just mix design, but going into pavement design and going into actually providing those at no cost to help with recommendations and suggestions on ways to be more cost effective in putting down pavements. So that's what we're here for. That's what we do. So I want to thank everybody for joining us, taking the time. Josh, thank you for this information. I do feel like there's so much to learn from this. Thank you for having all that knowledge and being able, I know you could have gone so much deeper, but you presented it in a way that we can actually understand it and learn from it. So thank you. We will try to make this available in a PDF and send it out. And if, again, there's anything we can do to help, please feel free. So at this time, I guess we can wrap it up, but we will stay here for questions. So if you have more questions, feel free to go ahead and throw them out at this time.
Thank you all for your time. I very appreciate it.
Looks like we might have one coming in. Oh, nope, that was a thank you. And
my pleasure. I appreciate it.
It doesn't appear there's any more questions, so I want to thank everybody again, and everyone have a nice afternoon. We'll see you next week.
All right, everybody take care. Thank you.